Hey class, let's go over some of the concepts of the two things we learned, 3.6 and 3.7. All right. 3.6 was implicit differentiation. So that was the fact that the derivative of y is dy dx. So that's pretty important because usually in their previous problems, let's say y equals x squared here, we always had y or f of x by itself. So we never had to really think about it too much. So this would be dy dx equals 2x. Since dy dx is by itself, that's nice and simple. But sometimes the y is not by itself, so we have to figure out ways to deal with that. Let's try this thing. Let's start with a basic, then I'll do one that involves chain, I'll do one that involves product, and maybe I'll do one that involves, I don't know. Let's do a basic one. Let's do y 10 equals 15x squared. Okay. In this case, I'm going to take the 10, move it down here. So 10y to the 9th. So in this case, it's a chain rule where 10, the power 10, is the outside of my chain. And then I have to do the inside part, which is the inside g here. So I have to times it by the derivative of y, which is dy dx. By the way, you technically always do this also with x, but the nice thing about x is that the derivative of x is dx over dx. I'll put that here. X equals dx over dx, which means it always reduces down to 1. That's why we never had to think about it before. So here I'm going to bring down 2. 2 times 15 is 30. X times the derivative inside, but since the derivative is 1, it's just 1. Or it just stays the same. All right, we need dy dx to be by itself, so I would divide 10y to the 9th on both sides. And I can see here I have a 30 and I have a 10. I could reduce that. So dy over dx equals 3x over y to the 9th power. Okay. Hopefully that's a basic one to show like a power of y. Let's do a not so basic one. Let's do like a product rule. Let's do 2x. Wait a second, I gotta get a charger. There we go. Let's do 2x to the 3rd, y to the 2nd equals 5. In this case here, we have a product rule going on where 2x is its own thing and y squared is its own thing because they're being multiplied to each other. So I need to use the product rule, which is g f prime plus f g prime. This is my f, this is my g. If you want to spend time writing on the side, that's fine. I'm just going to go right through it. G, which is y squared, f prime, which is the derivative of this, 6x to the 2nd, plus f, the original, 2x to the 3rd, times the derivative of 2y, which is 2y, now to the 1 power, dy dx. That equals the derivative of 5, which happens to just be 0. Remember, our goal is to get y by itself. So I'm going to subtract this to the other side. I'll rewrite it as 6x squared y squared minus 6x squared y squared. So then I'm left with 2x to the 3rd. Oh, 2 times 2, I should say. So 4x to the 3rd. So 4x to the 3rd, y to the 1 power, dy dx equals negative 6x squared y squared. Divide both sides by 4x to the 3rd y. Final answer, dy dx equals negative 6x cubed y squared. I mean, not cubed. X squared y squared over 4x cubed y. Hey, we could simplify some things. So your final answer, negative 3 over 2. There's an x on the bottom, and there's a y on the top. Let's do a chain rule one. Let's see. Let's do like a... let's do a tangent of y. So in this case, I need the derivative. This is my chain where this is the outside and this is my inside. Actually, let's up it. Let's do it to the second power. So this is f and this is g. Remember the chain rule is f prime of g times g prime. So here, I need the derivative of tan, that's secant squared. The inside stays untouched, so that stays y squared, times the derivative of y squared. Now the derivative of y squared, hopefully you realize now after doing it a couple times, 2y times the derivative of y, dy dx. That equals derivative 0, 0, 0. Okay. Now if you notice, all of this is multiplied to each other. So in this case, actually, I guess this is easy, right? Because secant squared, y squared, 2y, divided by all this, right? That's still going to be 0. So in this case, dy over dx equals 0. If it was like maybe like x squared or something, so it would be a 2x, the 2x would be on top. But still, the concept here is that you do a chain rule. The outside is the changing part. The inside stays untouched, then you multiply by the derivative of the inside. Let's deal something with multiple y's. Y squared plus 7y minus 11 equals 3x squared. In this case, all the y's are on one side, all the x's or everything else is on the other side. I guess I can move the negative 11 over here. No, I can't do it by itself. So let's plus 11 on both sides. And then all my y's are on one side, all my x's are on the other side, or everything else is on the other side. So let me derive each part individually. 2y dy dx plus 7, the derivative of y. I guess we didn't do, it's just dy dx, I guess. There's no chain rule. Equals 6x. This disappears. All right, since they both have dy dx, we could factor that out in common. So dy dx times 2y plus 7 equals 6x. Then we could have this by itself. Dy dx equals 6x over 2y plus 7. Remember, the goal for implicit is to get the y by itself, dy dx by itself. The y I don't care about anymore. I just care about the dy dx. Next one is the exponent rules. This is 3.7. So we have the generic log rule. Log base a of some x is going to become 1 over x ln a. Now, because it's ln a, if I have a log that's very specific, like the natural log, aka log base e, that means it's going to be 1 over ln x. So that's going to become 1 over x ln of e. But ln and e cancels out, so you could cut right to the chase, 1 over x. So ln's are actually really nice because the derivative of ln, you don't have to deal with the ln a. So if you start with ln, you don't end with ln. If you start with log, you end with log, or you end with ln. Maybe that's a way to easily remember it. And exponents kind of work in the same way. A to the x power is going to be x, oh wait, I'm sorry. It's going to be a to the x power times ln a. In this case here, though, if we have e to the x power, it'll be e to the x times ln e, but ln e cancels out, which means it's just e to the x. That's why e to the x power derivative stays e to the x. So let's do a problem. Y equals ln 3x to the fifth. In this case here, dy dx on the other side equals, this will become 1 over, ln is just 1 over x, so I could just write 3x to the fifth. But I need to multiply it by the derivative inside. The derivative inside here is, bring down the 5, 15x to the fourth, which means I could rewrite it as 15x to the fourth, 3x to the fifth. See, can I call you back in like 5 minutes?
And how long?
5.
Yeah, go for it.
So then, divide 3 on top and bottom, reduce the x on top and bottom, you have 5 over x as your answer here. Let's do a exponent one. 12 to the 5x equals y. So we're going to derive it. So dy over dx equals, since y is by itself, you're not really doing anything on the left side, you just focus on the right side. So it's going to be a to the x, so it stays exactly the same, 12 to the 5x, times the ln 12, times is going to be the derivative of this part right here. It's a chain rule because it's lumping inside something else. So derivative of 5x is just 5. Very important here, don't make a mistake. 5 cannot mix with 12 5x. These are definitely, they're different because they have different exponents. Like this cannot mix with this. So you only could write them next to each other like this. No combining. So don't be over eager in that sense. So one last thing, let's just do one that's like a mix. ln y squared equals x squared. Okay. So on the left side, I'm going to do the ln, which is 1 over y squared times the derivative of the inside, y, 1 over y squared times 2y dy dx. And that equals the derivative of this part, which is just 2x. I can simplify that a little bit, so it becomes 2 over y times dy dx equals 2x. Multiply the reciprocal, y over 2. 2's cancel out. So this is dy dx equals xy in this case. All right, hope this video helped, guys.